So this is the afternoon in India. Yeah, good afternoon everyone. So good afternoon, welcome to the third session of the third day. So today we have Professor Martin De Vos with us, and before we start, before he starts delivering his talk, so let me give a brief introduction about her, about him. Uh, yeah, Dr. Martin De Vos has a joint appointment as associate professor in the Department of Engineering and Medicine at KU Belgium, after being associate professor at the University of Oxford, United Kingdom, and junior professor at the University of Oldenburg, Germany. He obtained an MSc in 2005 and PhD in 2009 in electrical engineering from KU Belgium. His academic work focuses on artificial intelligence for health, innovative biomedical monitoring, and signal analysis for daily life applications. In particular, the derivation of personalized biosignatures of patient health from data acquired via wearable sensors and the incorporation of the smart analytics into unobtrusive systems. His pioneering research in the field of mobile real-life brain monitoring has won several innovative prizes, among which the prestigious Mobile Brain Body Monitoring Prize in 2017. In 2019, he was awarded the Martin Black Prize for the best paper in physiological measurements. He has a strong interest in translational research and co-founded circadian therapeutics with the aim to bring innovative home monitoring solutions to people suffering from sleep and circadian disorders. He has been guest editor for International Journal of Clinical Neurophysiology and Physiological Measurements. To date, he has supervised and co-supervised 10 PhD students to completion. And with this, I welcome Professor Martin to share your thoughts with us. So yeah, over to you, Martin.
Thank you so much for this kind introduction and also the kind invitation to share some of our work and methodology that we developed for, really talking about AI for sleep. But as already introduced, everything I do starts from a clinically relevant question. Based on my background in electrical engineering, I try to use data and devices that produce data in order to shed light into medical conditions. And so I just want to sketch a bit the scene of where we are now and basically where we want to be in 20 to 30 years from now. So if you do have a medical appointment, you basically visit a medical doctor, an expert, and he will ask you questions like, how do you feel? How did you feel last week? What's happening to you? Typically, he can't solve it. And what he does is he will refer you to maybe a medical scan, or he will monitor you for a certain period of time. But actually, you see already all these questionnaires and subjective explaining what is going on is very suboptimal in a world where basically we have a lot of measurement technology and ability to actually pinpoint what is going on. So I just state here a few limitations. It's subjective from the patient side. How objective is medical judgment? Basically, this medical expert has to integrate all this knowledge. Maybe two experts don't agree. So do we even think that the medical doctor in front of you is the gold standard? And then also in terms of optimal treatment, I hope you didn't experience it, but medical treatment is often based on we try something, we see if it works. If it works, it's great. And if it doesn't work, we will change the treatment. And so on and so forth. So basically, you see there is a lot of subjectivity and suboptimality in the way we do medicine, both in Belgium, but it's somehow across the globe. And so then you can even question, like, all this medical expertise, where it's coming from. It's actually coming from the expert experience of the medical doctors. So there is kind of this subjective bias embedded in the system. Medical doctors write their notes on papers. So basically, going back in time 20, 30 years, there were cupboards full of papers, medical notes, and things that contain all this knowledge that's passed on due teaching. But somehow now we do have digital electronic health records. So suddenly we get a lot of data and basically our mission is, can we harvest this data in order to extract clinically relevant information? Obviously, there is a lot of opportunity to improve efficiency, but also to improve objectivity. What we want to do is pull data from large populations within Belgium, but also across the globe in order to better understand medical conditions and applications. And so obviously, generating data is not enough. What you have to do is develop methodology that extracts information from this data. And so, yeah, the animations are a bit slow, but a lot of our work is focused on chronic conditions, because a typical chronic condition is represented here. You have the time axis, where you see basically over time symptom severity changes. You have a pre-symptomatic phase where basically you're considered healthy, and at a certain moment your condition might deteriorate. If your condition deteriorates, you will see a medical doctor. He will give you the treatment and you will go back to baseline. I think that, yeah, here we can continue. So this is one possibility of your medical condition. You get the medication, you go back to being good. But because it's a chronic condition, say asthma, COPD, Alzheimer, whatever, you will have a relapse and you will have your next checkup. There are other possibilities. You could, for example, have this condition that actually don't really get better. Or maybe if you have an Alzheimer condition, you might just get worse and worse and treatment not really affecting. But here, again, this idea about having one medical doctor checking you at a certain point in time is very suboptimal, because what we would like to have is measurements in between those medical personal checkups. And so we do have a lot of measurement technology, everything from wearables, smart watches, digital monitors, up to smartphones that can collect information about your well-being. It can be based on questionnaires. It can be based on how much steps you do. If you do move well, it can monitor heart rates, respiration rates, and so on and so forth. And so what I will be talking about today is also how can we use extra additional devices that can monitor brain activity. And so obviously you can monitor it in between the conditions, but in the future we might really think about how we can use the data on healthy people to start predicting what is going on with you in a few years. And in this way, we can start embracing the idea of doing preventative medicine rather than curative medicine. And so we do always ask a lot of questions. Can we identify diseases? Can we predict disease progression? Can we monitor medication response? And can we even start identifying what we call digital biomarkers and markers that really state if you're belonging to a certain group? I hear that there is a sound, but if you have a question, please do speak up, because I cannot monitor any chats.
Yes, Dipti, do you have any question?
Sorry, can you repeat?
No, I'm asking, Dipti, do you have a question? No. Yes, Martin, you continue.
Okay, so in terms of monitors that we have available, we have a lot. So wearable monitors, for example, this is a cardiac monitor. We have wearable cameras that can tell you about gait patterns. We developed a respiratory sensor that you can place in your bedroom in order to monitor asthma conditions. The smartphones I mentioned, you can have active tests where you can ask a person to do a finger tapping test if you're suspected with Parkinson's disorder, we can ask you on the smartphone to draw a figure 8. Again, it reveals about your neurological situations, and so on and so forth. We have lots of sensors information. So the point I want to make in everything what we do is, can we replace the old-fashioned system where basically you report to a medical doctor what's going on to being monitored by all kind of digital technology? And so digital technology, what it does is basically collecting information. Here you can think about a range of activities, a range of symptoms, a range of variables, and then you're putting it into a machine learning model in order to answer the relevant questions. Do you have a condition? Don't you have a condition? That's the continuous estimation question. How severe is your condition? Are you deteriorating or are you stable? And ideally, we would like to exploit also the longitudinal time components of the disorder. But as I mentioned already, basically, this is the medical context. If we translate this to medicine, to the mathematical modeling, the question becomes a machine learning or an artificial intelligence question. And we have two types of machine learning questions that basically are behind all this methodology. We have data, and we would like to predict a class label. Are you healthy or do you have a condition? Which condition do you have? Do you have one out of 3 conditions? This is what we call the class labels. And so the machine learning will extract them features, characteristics from the data, and learn basically a classifier that predicts which condition you have. This is when we have discrete class labels. Obviously, if you want, for example, to estimate disease severity, you're going to have a regression problem where you try to approximate a known severity of disease by the mathematical data. You still define features. Now we can call them regressors. And basically, rather than learning a discrete classification, you try to map it onto a continuous regression curve. So for me, it's all the same. I think what's typically happening during kind of a project or during innovation is that you start from defining features, you optimize your classes, you look at how well you predict on independent data by comparing the predicted class labels with some ground truth. And again, keep in mind the ground truth is the best medical ground truth we have, but we can debate how ground truth it is. And then you start optimizing your classifier, either by defining new features, changing the classifier, maybe even inputting new data. But in the good old days, all the intelligence was in the features. People were manually trying to extract good features, good characteristics of the data. This is the machine learning pipeline. Here again, I simulated with an artificial example where you say, my problem at hand is I try to discriminate between healthy people marked in green and Parkinson's disorder people marked in red. Some smart PhD students define a lot of features based on the available data, and you learn a simple classification in order to predict the outcome. In artificial intelligence, there's not much of a difference, but rather than explicitly go and defining the features, we define kind of a network where both the feature extraction and the classification parameters are learned all at once. So some people do differentiate between ML and AI. Personally, I think the question behind is how do we relate input to output based on a problem? And we can then start trying to use the latest technology in AI in order to approximate the output as good as possible. This is also where I took, just to put a bit of context on the mathematical learning. Basically, you can see this from left to right as different approaches, how we did data science over the past 20, 30 years, and basically how it's evolving. On the left, we have rule-based systems. Imagine you have a bit of insight in a condition, you have a bit of data. In the early days, the expert could just tell you, look, if your respiration rate is above a certain threshold, the chance of having a condition is high. This is a discrete rule. With digital technology, you can program this and basically have an automated system that does some medical decision support. What I call the classical machine learning is what I explained before. You have still your input data. You put a lot of intelligence in hand designing certain features, and then you try to learn a classifier that maps your features between input and output. Most of the more recent deep learning and representational learning says, like, how do we learn our features automatically? Rather than having intelligence in the features, we'll learn the features and the mapping together. And the really deep learning is, and I will give you some examples, is actually how you define ultra simple features and try to start combining simple features to more abstract features in order to learn the mapping. And so the more deep you go, the more you end into the deep neural networks, where you lose a bit the control of what features you're actually extracting, but we can derive good insights as well as very good performance on the task at hand. And I wouldn't say the right is always better than the left, but somehow from a mathematical point of view, you could say it's all the same. I already differentiated between classification and regression, but somehow you're always mapping your input X to your output Y. If Y is discrete, you have a classification problem. If Y is continuous or giving real numbers, you have a regression problem. And then so the question becomes, what is now my mapping function F? And you can just plug in available machine learning models. You can use logistic regression, you can use support vector machine random forest, and always learn the mapping and see how well you do on some unknown validation data. For regressors, the same. You can use deep neural networks and nothing changes. It's just that your function becomes a deep neural network. So somehow it's very simple. It's a few lines of code, and that's what I teach also our undergraduate students. But actually, obviously, it's a bit more complicated, because what we're doing is we're dealing with patients. And so patients are being monitored with certain data acquisition systems, and there are artifacts happening because patients are living beings. It's not just a digital system. Maybe there is missing data. You have to think about it. And basically also, ultimately, we have to present our data and our insights to the medical physicist, physician, the medical specialist, who has to present some insights about the patients and start some treatment. So it is very far. So although my former slide was a joke, it's all the same. From a mathematical point of view, it is all the same. But how to best apply certain artificial intelligence approaches to medical data requires a lot of insight into the actual problem and the understanding if your data is biased, what artifacts might happen, and so on and so forth. But obviously, popularity of AI is really growing. Lots of populations, and that is because we have more data. We have more data, we can monitor more subjects, we can monitor more variables, scanners become better, data monitors have a higher sampling rate, and so on and so forth. So obviously, machine learning and AI is being explored, but I always tell my students, start from the medical question. Do understand what is the medical problem, and not just do some AI on a database. Because obviously, it's very simple. If you have curated data to apply a method, you get some results. Mathematics always give you some results, but the question is, how do you make meaningful results? And so I spoke already about representation learning. Here is a deep learning. Why is deep learning in general so popular? 3 reasons. It's nothing novel. Based in the 70s, we had already some deep learning architectures and things and deep learning machines that could mine large amounts of data. But there are 3 things that really revolutionized the way we do deep learning now. First, the amount of data. As I mentioned, more data. But also hand in hand with having more data available, also our computational abilities increase dramatically. We have better hardware. We have GPUs that can harvest all this data. And also we have better algorithms to optimize the deep learning networks. deep neural networks. So basically, those three factors, they went hand in hand in order to achieve good results on a lot of on a lot of general applications, but also on the medical applications. And so typically, this is also something to keep in mind when you think, yeah, should I use latest AI or should I go more traditional machine learning? Performance dependent on the availability of data. Pure and low data regimes, traditional machine learning can outperform deep learning. If you're in very high data regimes and data is good quality data, you might think about going to deep neural networks. And keep this in mind because I will give you some examples where this becomes clear. And so when we speak about deep neural networks, probably the most common or the simplest deep neural network that is very powerful nowadays is a convolutional neural network. And I start here from the input, which is an image, and the output is basically your classification tasks. And what we do is we define several convolutions. In this case, 2D convolutions, and we compute this on the input. In order to derive the feature maps, you see here different layers. They can be different sizes of your convolutional filter, basically using different convolutional filters. And then you can use this convolutional filter to map the whole image in order to a new image. Obviously, you see you generate here, you use different filters. You do have a different size of feature maps. And so afterwards, what we also do is we're going to downsample. We get intermediate feature maps. We compute again convolutions. We have intermediate feature maps. We do subsampling and so on and so forth. And so every layer of doing convolution and a subsampling in some way is a layer in our neural network. In this case, we have 2 layers. Obviously, other applications do have more complicated layers. In the end, we typically have a fully connected network where we basically make, based on those final features, we try to derive the classification problem. So there are many more variants of the neural networks. I will give you some examples later on, but the most important is that you get a flavor. And so the intelligence in the AI becomes, how do you design a good network? How do you know basically that the network does a good job for your medical problem by exploiting some characteristics? And so you had yesterday a lecture on neonatal monitoring from Sabine van Huppel. I want to use just illustrate now a bit on how do we use AI technology for monitoring neonatal sleep. Obviously, I said the first thing to do is, okay, why would you monitor sleep? Actually, if you look at the evolution of babies between prematurity, the most premature babies born at 24 to 28 weeks, they barely show any sleeping patterns. Sleeping cycles start emerging around 30 weeks. And then when babies are maturely born, after, we can speak about having 4 cycles. Exactly, this evolution from having barely any sleep cycling to early sleep cycling to early binary sleep cycling between quiet and active sleep up to 4 sleep cycling is basically predictive for the outcome of the baby. So in the hospital, we are very interested to monitor brain activity of the babies, the sleep of the babies, in order to understand how their brains are doing. So translated to a deep learning model, basically to a classification challenge, is, okay, we do have, say in this case, 8 channels of EEG. We're monitoring premature babies. What we want to know is, are they in quiet sleep or non-quiet sleep? This is a classification problem. We have input data, the EEG, output, you're either quiet or you're non-quiet sleep. So what we can do is, and here I really want to show you how we go from this representation learning from the left, rule-based systems, to kind of the right, the deep learning representation learning, is our first algorithm quite some years ago really started making heuristic rules about the ongoing EEG. It was looking at bursting activity, consistent bursting across the different channels. Define a few processing steps. You see A, B, C, D, E, F, G, in order to extract kind of this cycling pattern that you see here in F about the brain activity of the baby across many hours. And you see there is kind of a nice cycling. So this is probably a fairly healthy baby because every 4 hours they are getting into quite an active sleep. Then you can threshold test, compare it with the ground truth, and you see this algorithm does a very good job in extracting quiet sleep. First approach, heuristic rules. Second approach, obviously we can also define features and learn a classifier. In this way, one of my PhD students, Kerwin Pillay, he looked into all the papers. Okay, what EEG features can I find in literature? He defined probably over 100 features. He discovered with machine learning approaches what I know the relevant features. Basically, he said, okay, I keep kind of the most relevant features, and then I learn a mathematical classifier. He explored a few ones, and he found that actually the Markov models, HMMs, or even GMMs, do a good job in predicting sleep stages, even going beyond 2 stages, trying to estimate 4-class sleep staging. So he spent probably a year or a year and a half trying to optimize parameters, trying to see which models were working well and which models were not working well. But obviously, the latest years, when we start, do we have enough data? We don't know if you have enough data. But what we know is that we can replace the algorithm with some more fancy algorithm, like deep learning. And so then another PhD student came and he said, okay, can I use deep learning technology? And he first made an algorithm for epileptic seizure detection in neonatal babies. And the algorithm looked like this. You see here on the left all the specifications. And I introduced a convolutional layer, basically a downsampling operation. You see here, it has several convolutional layers, 1, 2, 3, 4, 5, before he basically goes to the final fully connected layer. 5 layers, where it's already quite a deep network. You can wonder, okay, how did he optimize those parameters? Obviously, it was trial and error. He used part of the data to optimize a classifier, part of the data to validate this. And so this whole network he built, and it has 7,600 parameters. It's still not a very big network, but you see, even with a simple network, you quickly have a lot of parameters to optimize. This algorithm worked fairly good for seizure detections. Probably he spent a year on it. And then we asked him, okay, can you do sleep staging? And what he said, like, okay. And so obviously that's for seizure detection. So actually he did something very similar for sleep staging. The algorithm looked very similar. It's again a convolutional layer. The exact parameters are slightly different. You see, we simplified a bit the network. We went to 3,000 parameters. You see here convolutional layers and downsampling layers in order to make it work. And so the final output is detect quiet sleep or non-quiet sleep with a simple convolutional neural network. Results were very surprising. They were extremely good. So even if we didn't use any intelligence in designing the algorithm, apparently there was enough data that we had available to learn all the parameters. And so we have like over 90% accuracy across all the subject. And you see there are like a few outliers where sleep staging is completely different. Probably those are babies with a very bad outcome. But in normal babies, you do a very good job. And so development time of this methodology was only a few months. And basically, most of the work was spent on computational time and validating rather than really trying multiple models. So that's pretty good. We had a 2-stage quiet sleep detector, and then we could expand this also to 4 sleep stages. And again, development time was very little. What we did is we used the two-stage sleep classifier, and rather than having a binary output, we said, okay, can we compute 4 outputs? relating to the 4 different sleep stages that we would like to model. Not much more parameters in the network, but it did an extremely good job. You see, here you can basically compare our class model, the original heuristic one, with the CNN model. You do 10% better. Here you can compare kind of our HMM model compared to the proposed CNN for the 4-class problem. Again, you have a gain in 5% accuracy. Or this is even kappa value, which is even more impressive. So conclusion, deep neural networks do have advantages. Sometimes even development time can be shorter because you don't need to spend time on defining features and trying multiple classifiers. You start with a good network architecture, you optimize the parameters, and based on this, you try to you try to extract the relevant information. And so, just if the numbers don't tell you anything or you're not convinced that it's really good, here basically this is a sleep staging cycle, sleep staging from a hypnogram, what we call, made by the clinicians, and this is from our CNN, and you see that the correspondence, in once in a while, there is a bit of a mismatch, but overall the global sleep is very similar, demonstrating that we do have a very good network for neonatal sleep staging. So that's for babies. I'm going to give you another example on a sleep condition called REM behavioral disorder. In short, it's called RBD. And so actually, for those of you who don't know this, typically when you're in a REM state, which is one of the adult sleep stages, it's what we call the dreaming state. And during dreaming, your brain might be active because you're thinking about something, you're imagining you're somewhere, but somehow your body is relaxed. You don't have any your body is relaxed, so you're not making movements, you don't have EMG activity. During RBD, you see here in the animation, the person suffering from RBD will, during his dream, enact his dreams. So he will have violent movements, typically characterized by the partner who will suffer from, for example, beating or shouting or something like this. Again, an ideal case to start using data to monitor. And so in a sleep laboratory, what they will measure suspected sleep conditions like RBD or other ones. They will measure different physiological parameters, EEG, EOG, and EMG. And so during REM stage, you might see in the EOG fast eye movements because your eyes are jumping around. And during REM stage, rapid eye movement is basically what the REM stage is capturing. But then, as I mentioned, during healthy REM sleep, you have almost no EMG activity. However, those RBD subjects, you suddenly see here in the black trace that there is a lot of activity. So the question for us engineers was, okay, can we make an automated system that detects RBD subjects? This involves 2 questions. Once we have to detect, okay, where is the REM stage during the sleep? And second, when we have the REM stage identified, can we detect muscle activity in those subjects? And so, in order to get the sleep stages, basically, it's called a hypnogram. This is how it looks like in a healthy person. So you see, this is obviously a textbook example. In reality, it looks a bit different. But if you sleep 8 hours, basically, at the start of the night, you go into deep sleep. You do have a few sleep cycles across the different sleep cycles. You have less and less REM sleep, less and less deep sleep. But towards the end of the night, you have more and more of this dreaming-like REM state. The question is, can we approximate this with an automated machine learning approach? And obviously, the answer is yes. We have input data, EEG, EOG, eventually EMG. We can extract features. There is 20, 30 years research on defining features and using a machine learning approach for this job. The second challenge then, and we used simple features and a random forest classifier. We will get back why we don't use deep learning. What you see is then the second step is how do we quantify the EMG activity? And again, if you see the difference between the absence of EMG activity and those big EMG fluctuations, it's very easy to use some measures like variability in order to basically extract how much activity is happening in the EMG. And you see that an automatic system has above 90% sensitivity, above 90% accuracy in detecting RBT. Very good sensitivity, very good specificity. So somehow having the subject laying the clinic, putting on all the sensors, having someone to review all those 8 hours of sleep, then deciding if there is RBD presence or not, we can almost perfectly replace by an automated system, which is promising. Just again, to give you a few examples, here is the hypnogram of a real subject, a healthy old subject. You see it looks less perfect than in the textbook case. In the RBD case, it looks even erratic, but you see that in red, the automated sleep stages that we estimate fairly well resemble what the clinicians annotated. And again, this is based on features. The second stage, I gave you already the result, but basically what we did is we quantified some characteristics on the EMG. What we did is we defined features like stream, like amount of motor activity, and an atonia index. So basically it's an index capturing the lack of motor activity. And you see all those measures correlate very well between the annotated sleep stages and our automated annotated sleep stages. So basically, our automated sleep stager doesn't change the influence of motor activity, and we can use this full system in order to make an RBD system. But this example I use to illustrate, actually, it's great we can do this, and we can fully automate the labor-intensive process, which is happening in a sleep laboratory. But you also saw that you need to record EEG, EEG, and EMG in a hospital system, because that's where they have it. So actually, where we want to go is to be able to do sleep analysis in a home environment. And going back to my introduction, we want, in an ideal world, to have accurate sleep interpretation at a daily basis. Longitudinally, when sleep deteriorates, a chronic condition might also be deteriorated. Yes? Is there a question?
No.
Okay. So the question then becomes, can we use all this automated AI in a home environment? And here are two aspects. One is how can we make sleep staging even better? Second one is how do we do this at home? And actually, I mentioned in the RBD case, we relied again on features and a classifier like random forest. It's a good, robust approach, but it doesn't. It doesn't take into account the nature of our signal. Somehow, this approach is an example of what we could call a one-to-one classifier. We have one epoch, one label, and we use the label, the information in this epoch in order to make a prediction. But somehow, sleep staging, as you saw, is kind of a very slowly changing output. So here, you can say the one-to-many. If I know I'm currently in a deep sleep, probably my former epoch was also deep sleep, and my next epoch will also be deep sleep, because it doesn't change at the level of an epoch. Also, the opposite is true. You can have a many-to-one approach. So you can use contextual input in order to say, like, if my previous epoch, in order to make a prediction on my current epoch, I can use features from the previous epoch and features from the next epoch. And obviously, if you can do one-to-many or many-to-one, you can also do many-to-many and use kind of a sequence of features in order to do predict a feature of output. And this is actually so while traditional classifiers like random forest or SVMs, they can deal with something like a many-to-one by increasing the amount of features. Such sequence-to-sequence networks have an elegant solution in deep neural networks. And so this is what we then try to build is really a deep sleep staging, relying on not a convolutional neural network, but a recurrent neural network. So a recurrent allows to embed a bit of time information. And so we start from a series of epochs. And actually, we even use 20 epochs, and every epoch is 30 seconds. So we use about 10 minutes of data in order to build a neural network that predicts the instantaneous layer. So we used filter bank layers. So basically, it's an RNN interpretation. Here we have our recurrent layer. Basically, you see in arrows. Don't try to grasp all the ideas, but basically, I want to give you, basically, it tries to capture the dependency of the different time samples within one epoch. And then on the next level, we can use an attentional layer to say, okay, which parts of the signal are most informative. We can add another recurrent layer where we basically try to map the dependency of different epochs on each other in order to make a sequence of outputs. And because we start with 20 input epochs, we can also make 20 predictions at once in the output layer. That's great because if we have 20 output layers, on the one hand, we can do it faster, but also when we shift our epoch by one, ultimately we have 20 predictions for each epoch, and we can make our output more robust. So the output of this network is then again the sleep stager, and what we saw is actually that if you use a large database, a large is here like 200 subjects, for example, healthy subjects, then you can improve from a feature-based approach that has 80% accuracy to our deep learning model, which is almost 87% accuracy. So again, you see a big jump, and somehow, obviously, we spend a lot of work trying to extract insights, both on how is sleep staging done, what information is available. But once you have the network, basically the parameter optimization of this network is done fully automatic based on the data. And so here we are really into the AI world, while in the AI, so showing that deep learning methods, representational learning methods, can extract relevant information from the data. So this network, we called SEC-SleepNet, Sequence Learning Sleep Network. And that's basically still one of the very good networks nowadays, although we introduced it 3 years ago. And just to show why it is good, that if you use it on a completely different data set, and this is the data set recorded from EEG signals within the ear canal. I will come back to home monitoring, but you can imagine if you can pick up brain activity from within the ear, then you can also try to do sleep staging, and we evaluate the different recordings and things like this. But you see overall, again, you get good kappa values, and we use the same SEC-SleepNet, just optimized on a different data set. So somehow this validation on external data sets, just not showing that it works on one, but we just apply it in a completely different setting, and it does a great job without any adaptation. So for us, that was great. But then we want to go, obviously, I would consider SEC-SleepNet the state of the art. But you can always do better. You can always think, okay, what specific characteristics are available in sleep data? And for example, if you think about longitudinal sleep monitoring, you don't want to have one pre-trained model. You know, if you have multiple nights of sleep monitoring of a certain subject, you can use this information in order to improve and personalize your model. And that's what we say here. If we have a certain night of a certain subject, we can add this to the training phase. We can add this into the modeling in order to update the model for staging the next night. There's not so much data available, but some subjects have 2 nights in the hospital, so we can simulate this. The way we do this is by transfer learning or fine-tuning. We keep the same model, but we optimize a few parameters in the model. We retrain a bit. We use the initialization, but we retrain a bit. And so we keep the same architecture, but for every subject, we have different parameter values to be used. And this is then on 3 different databases, how personalization works. Basically, all the measures on the spider grid are just quantification methods. We have a kappa, we have an F1 score, we have an accuracy, specificity, sensitivity, all those. And you see that our latest models, our personalized models, always do better. Personalizing, you can also look, this is on a database where we have 2 nights. So basically, we have 1 night that we can learn the personalized model. And then on the second night, we can show the advantage of having a personalized model. We have 75 subjects here. We ordered them based on the initial sleep staging performance. What you see here is the personalized, the accuracy of the model after personalization. But most interesting is here on the bottom, you see the relative improvement of the model after personalization. What you see is here, obviously, we have here the worst subject and here the best subjects. And on the best subject, personalization doesn't has a lot of impact. As you see, overall, there is barely any improvement. It shows they have representative sleep. However, you see on all the almost all the subjects here, which have initially a bad performance, doing some personalization helps to improve the sleep staging with an average 10%. So while personalization might not be needed for everyone, it can really do a good job when initial sleep staging performance is not ideal. And you can imagine disease people suffering from certain sleep disorders will be here because they have different sleep, they have worse signals. So having a bit of optimization within the network can really help. This is, I mentioned sex sleep map is for me state of the art. Obviously, we always try to boost a bit of performance. In this case, we also developed XSleepNet. And again, I don't have the time to go into all the details, but I want to give you a glimpse of the idea, what we used. It's actually a very nice conceptual paper too. So our sex sleep net starts from time frequency representation of the signals. Other people have built models based on the raw data. So the question is then, how can we now, why would we start from time frequency input, other people from raw sensor signals? Why don't we do both? So this is what we thought about. Okay, how can we build a network that integrates the best of both worlds? And so we thought about design principles of building a new network. And we said, really, the input data should be very complementary. It doesn't make sense if you just have the same input data that you build 2 networks and you hope it does better. The more diverse input you have, the better. So that's why we said, can we combine the raw data with the time frequency data? The second thing is also, we want to monitor which of the 2 settings is currently overfitting and which one is currently generalizing. And so rather than simultaneously learning those one-to-one, just in parallel, we continuously monitor the network in order to see which one is generalizing well. If one is generalizing well, we further optimize it and we don't pay attention to the network stream where you're overfitting. Overall, so basically, this is then how it looks like. It's still a sequence-to-sequence approach. You see, you have many input epochs, you have many output epochs, but basically for every epoch now we have a prediction from our time frequency network and a prediction from our raw data network. But I say, you still see here the big recurrent neural networks, but the way all those parameters optimize is not all at once. We continuously check how to ideally optimize those. And again, the representation I also used before. On different databases, we can see that the new networks, the XLeapNet 1 and 2, they just differ a bit in how we optimize the two streams, do outperform kind of our current SexLeapNet, which is basically the blue and the green are the initial networks, the red are the new networks. And you see that you gain always a percentage or a few percentages by increasing the accuracy. I think this network is a very nice engineering innovation. Having this 1% extra accuracy might not be needed for clinical practice. It's always depending, does it have a big impact on the clinic? Who knows? Not to be seen. And obviously, we keep making new models. We currently have a sleep transformer. Transformers are very popular in current AI research. They use attention focus in order to see what's most relevant. We also have better results with them, but again, it's marginally. It's in the 0.12% when we have a data set of 3,000 sleep recordings. And you'll see the gain we get from better models and more better models, or say more sophisticated models, which can translate to having more parameters in the model, is following the law of diminishing returns. So making an even more complicated model doesn't give you an equal boost in performance. Why do I show this slide? Actually, there are two aspects that we can monitor. Obviously, you recognize here the hypnogram, the output of our sleep staging. Here you have in the lowest row, you have the ground truth. You see again, those models really mimic very well what the clinician said. With the red crosses, we mark the discrepancies. You see often they're just at the change point, so it might be one epoch later or earlier. Here also, you just have a change. Sequence to sequence approach ignores it because it thinks like this one epoch is not relevant. So overall, you have an impressive accuracy with this network. But also, we don't think like the ground truth is really the ground truth. It is not that from 1 second to the next, you change from one sleep stage. Well, it's more a continuum. So we like kind of outputting a probability of the different stages. Initially, you have a large probability of being awake, but at the transitions, you do have a probability of transitions. So you can see maybe you're definitely in REM, but here maybe you have a bit in REM, but you might also be awake in one. You see then adding this information to a clinician really helps to basically add information rather than just looking at these finite sleep stages. And moreover, we want to reduce the burden of the visual scoring. So it's not our goal to make an exact replacement of the clinician, but we want to integrate our methods for the clinician. How do we do this? By also adding confidence. If we are very confident about the AI input, AI output, the clinician doesn't have to look at it. However, sometimes there are periods that the AI says, okay, I'm not very confident. And what you nicely see is that actually the periods when he is not very confident, we make some mistakes. Here also, you're not very confident. You make quite a lot of mistakes. So somehow it's this idea when we can focus the attention of the clinician to those regions where you say, okay, very different sleep traces. Please take a look. And so you can reduce the effort of the clinician to focus on difficult parts. And maybe he revises it, maybe he says it's irrelevant. But so you can gain a dramatic improvement in time of reviewing the data. And I'm seeing that I'm a bit behind schedule. So I'm not gonna. You can take a look at the sleep transformer paper if you're interested. How we can also try to add some visualization. But you see, adding a visualization becomes even a pretty heavy task here. But in summary, for sleep monitoring, deep learning, because we have so many public databases, does a good job. We've shown that this many-to-many architecture does take into account long time information embedded in the EEG. Having multiple outputs makes the network pretty robust, so we are at the stage that we can translate this into clinical practice. But this is it's a very nice innovation on the engineering side, but the real breakthrough is still a bit further. The real breakthrough is basically how can we monitor sleep outside of the laboratory? Can we do this at home? And that doesn't only need this automated AI technology, it also needs new EEG technology. This is how it looks when you go to a sleep lab. You get all those electrodes glued to your face. It's not comfortable, it's not looking nice. So we were exploring a range of solutions. And so this is one of our electrodes arrays that we explored. They were at unconventional places. They're not on top of the head where you typically measure the EEG. We said come behind them, behind or around the ear, and do automated analysis. And what you see is actually that manually looking at such new electrode positions don't do a good job. So this is the annotation, the accuracy and the Cohen's kappa of manually annotating this data. And it's true, clinicians are trained to score electrodes on top of the head. They're not trained to score those different derivations, and they might also suffer from more artifacts. What you see here is that if you automatically analyze the data in the hospital, you get a fairly good Cohen's kappa, as you expect, because we do have the AI technology, but it's as good as you automatically analyze what we call the secret, this new derivation. So again, there's a lot of promise to start taking those results out of the clinic. Very similar to what I showed on the in-ear electrodes, where if you measure in the ear, you use automated AI, you do as good as with traditional recordings, with all the advantages associated to those new recordings. And so obviously you wonder, okay, how do you get to such derivations? I was interested for long term into mobile and wearable EEG because we said measuring EEG activity, as shown in the picture, that's really old-fashioned. They don't allow you to walk around, to move. So we started developing the first mobile EEG amplifiers to say like, okay, how can we bring the EEG out of the lab? We can miniaturize EEG monitoring. We can make them wireless. We can even record them on the smartphone. But then you still see that you always are bounded and limited by this electrode cap. So we also started exploring, can we place electrodes in audio devices? Can we place electrodes around the ear? Or can we use such flexible electrodes, which are currently developed in Israel, that we can just glue to the face? Because again, you see we're exploring non-hairy situations. The difference between our cigarettes is that we still use electrode gel on those flexible electrodes. They're fully foldable and they don't need electrode gel anymore. So you can imagine a miniaturized system where you just stick it in the evening on your forehead. In the morning, you take it off. All the data automatically sent to a smartphone and automatically analyzed by the AI system. I mentioned this already. If you have those derivations, it's harder for the human scorer. It's as easy for the automated AI system to analyze those data. So we're really, this is the same picture. So the last challenge I want to talk about, when you really talk about sleep monitoring with wearables, what I showed in the previous slide, is that you do as well with new recordings as with PhD. There was one limitation. We used a lot of recordings, and we needed the recordings both in the lab simultaneously measured with a new recording. Otherwise, we don't have the ground truth labels, and otherwise, we don't have, if we don't have enough data to optimize it, we can't learn the model parameters. However, we're iterating different devices. Sometimes we're placing novel electrodes, we're adding electrodes. That would require that we all the time do a new AI optimization. So we have the PSG, we have a new device. The question is, can we immediately get the sleep staging? And so I introduced already the idea of transfer learning for personalization. You can use information learned from C3 to transfer this to a different electrode position, either for frontal electrodes or for behind the ear electrodes. But the question becomes, how many subjects do we need? Can we do this just based on 1 or 2 subjects? Because then we can just optimize the algorithm quickly and do a good generalization performance. If for every device we need like 20 or 50 subjects, basically it's very suboptimal. So transfer learning, fine-tuning, is just adapting the weights. However, we thought, can we also design a new model? Basically, that's fine-tuning. What I said, you have your input data, you have your output data, sleep stages, feature exact classification layer. This is all your deep neural network. If you fine-tune on a target, on a different derivation, you just transfer the weights and you optimize them a bit. So what happens on a feature space is that, okay, you adapt the boundary, you adapt the features a bit, but you kind of forget what's happening on the initial data source. We thought this is suboptimal because we forget about the original data, and we also don't exploit this correspondence between data sources. What we said is we can develop a network, which we call feature matching, where we replicate these stages based on our original data, our new wearable data. We have this pipeline twice, and we add a cost where we try to minimize the difference between the source and target features. The source are the original EEG features, those are the wearable features. And what you see then is that in the data space, we only monitor small shifts, and we don't lose the accuracy we have on the original data. In summer, it's a really nice model where we don't need lots of data in order to optimize sleep staging for wearable devices. Obviously, I've shown here the sex sleep net. We always rely on this because it's the state of the art for us. And we said, okay, how much training data do we now need to generalize well? And that's what you see here. If you would retrain from scratch, you do a very good job. If you did directly applied your model here on the right, you drop over 10%, which is not a good stager. But by adding 2 recordings or even 5 recordings, you dramatically improve either by fine-tuning or by feature matching. But you see that both for 2 and 5 recordings, the new model, the feature matching approach, does a much better job than the fine-tuning. That's a really nice approach where you basically use the structure of your data, use the correspondence in order to optimize model performance. And so I'm coming to the end. I hope I gave you a bit of insights into both clinical monitoring, sleep monitoring, as well as how AI can be used to analyze those data. But I basically have a longer, still like at least 10 slides on some reflections, because I think that's as important as showing good results. And we're running out of time because I want to leave enough time for questions from your side. But I think it's very important that what I said in the beginning, we don't apply AI just because there is a data set available. And also, as part of this systematic review on the COVID-19 papers, you might have seen it's a completely different setting, but suddenly, since COVID-19, a lot of people started measuring aspects. And a lot of people started analyzing, doing better detection, doing better diagnosis, doing better prediction. People started quickly publishing, but when we started reviewing these papers, it was all as quick as we can. We have a bit of data, we have a model, we show the values. And it doesn't make any sense if you have a model with 87% accuracy. You need to really consider all the design considerations when you do model development. And so what a colleague of mine said, like, okay, sometimes people claim AI will solve everything, big data will solve everything. Keep always a critical eye on it. It's not that AI will always have better generalizability. It's not that it's always better, the classical modeling. I can give you as many examples where the classical ML is still outperforming the more modern deep learning examples. And so this is one of my things. Don't jump to conclusions. Always think, what is your medical research question? Do you have the right data? And does your data have good quality? Here's the cartoon. It's not because you can do something that you should do it. You should first think where you want to get. Do you have the data? And can you learn from it? And so this is also just a cartoon to kind of keep in mind, okay, what might be relevant, what might not be relevant. If you think of buying a Porsche, probably that's what you're dreaming of. Thinking about a very fancy car, fast, shiny, and things like this. If you don't want to pay for it, probably you might still find a Porsche. It's probably going to look like this. And exactly the same applies for developing risk models, for developing AI models. If you want to get, you're not paying with money, like in the case of the Porsche, but you're paying with sample size. You're paying with data. Flexible algorithms are data hungry. Keep in mind, you need data, you need good data. And only you, when you understand the medical problem, can say if you have the relevant data and if the relevant data can be acquired. And in sleep staging is a really nice example because we have so much data available, we have so much annotated data sets, but still there. But still, for example, you can't apply it directly to, I would say, Alzheimer patients because their sleep looks completely different. And you can again question, did we have the right data to solve it for Alzheimer patients? So it's all about the data. I can give you more examples, but as I mentioned, I think I want to end here by thanking all my former colleagues in Oxford who contributed to this research and my current research group in K11. And then I would say, happy to answer any questions you might have.
Yeah, so thank you, Martin. That's really a wonderful presentation. But yeah, first I would like to take questions from the audience, from the participants. Yes, anyone having questions? Yes, Martin, if you don't mind, can you please go to your slide number 23?
Okay, yeah, I will.
Yeah. So I just have a question. How did you optimize the parameters?
Wait, my computer is. I'm taking the slide 23. So that's the slide on the CNN parameter.
Yeah,
So
yeah.
in AI modeling, I didn't go into detail because I mean there's a lot of algorithms available there and a lot of nitty-gritty details. But typically we initialize them in a certain way, and then we use a technique called backpropagation. So we always evaluate at the current set of parameters how well we do. We compute what we call a cost function, and the most classical is a cross entropy cost function, but obviously there are many variations where we, for example, compare the difference between the actual ground truth and current estimates. Obviously, there is going to be a difference. So we're using gradient descent or boosted gradient descent, accelerated gradient descent, all kind of different ways to basically speed up the way we converge to a better estimate. And then we reinitialize it. And so we iterate a few times. In deep learning, we typically use batches. So because you can't optimize everything at once, we start chopping the training data in smaller batches. And we every time optimize the network based on a certain batch. And then we iterate also across batches. As such, it's a non-convex optimization problem. So initialization matters. Typically, we have to run the algorithm a few times, but we nowadays have very good optimization techniques to make it fairly robust for training such convolutional neural networks.
Okay, yeah, thank you. I have another question on RPD problem.
Slide?
Yeah, RPD. I don't remember the slide number.
Wait.
Yeah, RPD.
Sorry, I don't hear the number.
Yeah, RPD. I have another question. Yeah, RPD. I don't remember slide number. But the question is actually, so if we have, let's say, so can't we use some blind spot separation problem in this case?
Probably, but it's an interesting idea. But in sleep staging, we don't have many recording channels. We typically have between 2 and 4 EEG channels, and then one EEG, one EMG. So there are many activities simultaneously ongoing, but you can't really separate them into contributing sources because you don't have enough sensors. So that's why we really have to use a machine learning approach, just trying to look at the joint activity that we observe.
Okay, so yeah, because we are recording on babies, sorry, we have only 3 to 4 channels.
Yeah, exactly. Also, there like the typically adult EEG, they have high density, and there I see is a very nice tool. For babies, you have 3, 4, at most 8, which is not enough for long-term recordings. And also in sleep, we have few channels, and also in home monitoring, we try to have as little channels as possible. So we have some data sets with also 4 to 8, but our mission is to do it on 2. And that's why we don't invest in blind source separation techniques.
But then can't we use some heuristical methods?
So some which method?
Heuristical methods, yeah, rule-based methods.
You can, but because we have so much data, we can show that the deep learning really outperforms. So, and that's also kind of the message I gave. We typically first start from rule-based or simple feature-based methods, and only when they have kind of defined a baseline, we can see if deep learning works. It's never a good idea to just take a data set and do deep learning, because you have no idea what are the problems of the data set, how complex is it, how much variability do we have, and things like this.
But whenever we use deep learning or CNN, then yeah, how to convince to the factors, because features, yeah, we don't have interpretable or explainable features. So how to convince to the factor?
Yeah, absolutely. I mean, there is the trade-off between model accuracy and explainability. We also work on explaining deep learning models. It's far from a closed research topic. So I think more work is needed to really use the good performance, and then and start. But yeah, it's a trade-off. I really see it as a trade-off, and I'm more in the favor of achieving good accuracy and doing them live.
Yeah, as an engineer, we are interested in numbers.
Yeah, but also for the clinician, I don't want to give just a classification result, but I want to give a classification with a confidence. So if I or my machine learning is confident, I would trust it. But I'm not always confident, so I would say, like, look, 80% of the time I'm confident, just trust it. And then this 20%, I'm less confident, please review it. And then you have kind of a win-win, because you save a lot of time, and you don't have to really bother about the explainability, because they will anyway review the data.
Because
but that's my point. I mean, other people believe in more explainable models.
Yeah, so because whenever we submit a paper using deep learning or CNN, and if the paper goes to a clinician, they are asking this kind of question.
Yeah, but I often get this question, and they always think they often come from people doing people not trusting deep learning or not liking it. But then I always ask, like, okay, if you do have an entropy feature and you use a classical machine learning approach, I don't think any medical doctor knows what is entropy. So even if you have like a certain weight to an entropy feature, you might call it explainable because you can assign a weight to a certain feature, but in my opinion, it's not explainable either. So it's just the viewpoint that you take there, and
I got it. Okay. Yeah, yeah, I got this point. Yeah, regarding database, are these, yeah, some of them are in public database.
yeah. But in sleep you have a lot of public databases. Also in neonatal sleep, there is one public database, and obviously we also work with local hospital, and it's mainly due to ethical issues that we cannot share some of the databases.
Yeah,
Because if you work with preterm babies, if you know when the recording is being done and what's the age of the baby, there is a high risk that you can identify the person. So like ethical commission doesn't allow us to share it. But in adult sleep, I mean, there is not such a risk, so we share a lot of data.
yeah, for adult, yeah, there are plenty of data.
Sorry,
No,
I
no.
didn't.
For adult case, there are plenty of data.
Yeah, there's plenty.
Hmm. Yes. Any questions from others?
Yes.
Yes, Sankaran Lakshmi. Do you have another? Do you have any question? No. Okay. Okay. I don't think there is a question. But yeah, I have another question regarding cancers. Yeah, because I know you are working on, you were working on the cancers. Yeah.
Yes.
Uh, so yeah, can't you use those methods? Because I'm right now actually I'm working on seizure detection. I have started. Uh, so probably in 1 month I will be in touch with you. Yeah, I'm working on seizure detection. Yeah, but yes.
Yeah, that's interesting. Yeah, we also work on seizure detection. Uh, Always curious to hear what you're doing.
Yeah, so maybe in 1 month I will be in touch with you and Bori. Yeah,
Absolutely.
regarding seizure detection using tensor decomposition. Uh, okay.
Nice. I'm looking forward to it.
Okay. Thank you, Martin, for this wonderful session. So, on behalf of the organizing team, so I thank you for finding your time for us from your busiest schedule. So it was really an interesting talk, and so
Yeah,
I'm
if
sure that
anyone has further questions, they can always reach me. So,
yeah. So I think participants have already your email ID. So if they have any queries in future, they can mail you. Yeah. So on behalf of the organizing team, again, I thank you so much. Yeah. Thank you so much, Martin.
you're very welcome.
Yeah, I'll be in touch with you in 1 month regarding
Yeah.
problems I could deal.
Thank you. Have a great session.
You
Bye.
too. Okay, bye. Yes, Jagannatham, I think I've already shared the schedule with you. So tomorrow again we have um, we have three sessions